Hi, I'm Nicola Messina, second year PhD student at the University of Pisa, actually collaborating with the Artificial Intelligence for Multimedia Information Retrieval group at the Institute of the CNR. In this work, I will introduce my PhD research, Relational Visual-Textual Information Retrieval, with advisors Dr. Fabrizio Falchi and Dr. Giuseppe Amato. I will begin with a brief outline of the presentation. First of all, I will discuss why relational understanding is a key component in modern cross-modal information retrieval systems. Then I will present a preliminary work in which I introduced the relational content-based image retrieval task. Afterward, I will consider sentence-to-image cross-modal retrieval on real-world images using natural language sentences as a query to retrieve pictures. Finally, I will try to grow on these ideas, laying down some proposals to develop efficient methods for scalable yet effective cross-modal retrieval systems. In the end, I will throw some conclusions, and I will present interesting and challenging future directions for this research. Modern multimedia databases are composed of billions of textual documents, images, and more recently, even high-quality audio and videos. With the huge growth of such volume of data, intelligent and scalable systems are needed to link together all this multimodal knowledge. One of the main reasons to make this knowledge converge is the possibility to perform complex searches involving different modalities. For example, finding pictures using some natural language description or finding the text in a document better describing the slice of a video. To do this, a complex and high-level understanding of the multimedia elements is needed. Two kinds of relationships exist among multimedia objects. Intra-element relationships, where two different parts of the same multimedia element are linked together by means of semantic or spatial relationships. For example, the soccer player and the kicked ball in the image, or the word his refer to player number 29 in a text. And inter-element relationships, where information pertaining to different modalities is matched. For example, the phrase player number 29 and the image region describing the player, or the phrase soccer ball with the region identifying the ball in the picture. Note that in this example, also the word kicked, that is a verb, has a grounding in the image as the intra-object semantic relationship between the player and the ball. Intra-element relationships are needed for an effective unimodal retrieval. I will address this problem in the next slide when introducing the novel relational content-based image retrieval task. On the other hand, intra-element and inter-element relationships are needed for an effective multimodal retrieval. We will tackle this very interesting problem later when addressing the sentence-to-image retrieval task. To address this problem, the objective is to create a compact relational-aware visual feature, able to describe not only the visual content, as many works already did, but also able to deal with the relationships between the salient objects in the image. A proper relational benchmark is needed. In this work, I used images from a challenging dataset called Clever, which collects images with simple 3D shapes in different spatial configurations. Being synthetically generated, they come with their associated scene graphs, where every node represents an object and the edges represent the spatial relationships connecting them. Although this is far from a real-world dataset, it is used for testing the basic working ideas in a fully controlled environment. Clever has been originally designed for solving the relational visual question answering task. Relational visual question answering consists in answering articulated questions involving abstract relational capabilities on counting, comparison, and spatial arrangement of objects in these images. I built on the assumption that architectures able to correctly solve the relational visual question answering task are able to internally generate some informative visual features, embedding enough relational visual knowledge for solving the downstream relational visual question answering task. These kinds of architectures can be used as good relational feature extractors for the RCDIR task, in the same way as object classification networks are used for extracting standard non-relational visual features. Starting from the work by Santoro et al. That developed a relational reasoning module solving the relational visual question answering task on the Clever dataset, I extended the architecture to extract a compact relational visual descriptor. I called this architecture Aggregated Visual Features Relation Network. More in detail, the first part of the architecture is composed of a simple CNN extracting features for every spatial position. Then a relation network model uses these representations to create features describing every pair of objects. This is obtained by concatenating every pair of features in output from the CNN and then processing them using simple feed-forward networks. All these features are aggregated at a certain point in the visual pipeline using symmetric functions, average or sum. At this point, the question embedding obtained by using an LSTM network is concatenated to the obtained visual feature and used to infer the answer. I used L2 distance to measure this similarity in the feature space for ranking the top relevant images. I prepared a relational ground truth for demonstrating that the extracted features can incorporate important relational details, and I did that using the scene graphs associated to every Clever image. I prepared the ground truth, obtaining the top relevant results for every query image, using the graph edit distance computed between the scene graphs of the query image and the scene graphs of all the others. The graph edit distance guarantees that the distance is computed by keeping into consideration the spatial arrangement of objects in the scene, and therefore this distance inherently incorporates relational insights. The values in the table report the sperma row correlation index with respect to the ground truth ranking obtained using scene graphs. Relatively to two versions of the Clever dataset carrying different numbers of objects per image, our relational visual feature obtained the best results in terms of ranking similarity with respect to the baselines. In particular, it obtained best results with respect to the vanilla relation network architecture and with respect to the state-of-the-art in standard non-relational content-based image retrieval, the RMAC features. Until now, with relational content-based image retrieval, I considered a unimodal intra-relationship system. The next step is to consider a multimodal system. In this case, I begin handling intra-element relationships between visual and textual modalities for the task of sentence-to-image retrieval, where the objective is to retrieve images using natural language text. Also, differently from the RCBIR setup, where I used only computer-generated images, in this scenario, I moved to full real-world data. Sentence-to-image retrieval is strictly linked to the challenging task of image-sentence matching. Given a ground truth composed of images and related human-written sentences, global features are extracted and images and sentences are matched into the same common space by using weak supervised machine learning approaches. The main objective in this task consists in bringing together related text and images while pulling away non-related pairs. This is usually performed using a hinge-based triplet ranking loss. In the formula, I and C are the matching image and sentence features, and I prime and C prime are negative image and sentence features sampled from the mini-batch. S is a similarity function. Usually, the standard cosine similarity is used. Once the training is done by using the same similarity function S, the features in the common space can be used to measure the similarity between a text and an image. In the sentence-to-image retrieval, a relevant list of images for the text-driven query is returned by sorting the images by decreasing similarity scores. Current state-of-the-art approaches for image-text matching make use of attentive architectures, able to spot out hidden intra- and inter-element relationships. More in details, they extract a variable set of region features from the image and a variable set of words from the sentence, and then they perform inter- and intramodal relational reasoning using the power of transformer encoders. Self-attention in transformer encoders learns hidden intra- and intermodality relationships by internally constructing an attention matrix that relates every word or region to all the others. These self-attention modules take inspiration from the BERT architecture, which obtained state-of-the-art results in natural language processing. Although these architectures can obtain very effective results, they cannot be used for efficient sentence-to-image retrieval, as the visual and the textual pipelines cannot be independently forwarded. This makes it impossible to separate the offline indexing phase from the online search phase, as the online matching function producing the similarity score is too complex to be evaluated in few milliseconds. They can do sentence-to-image retrieval only by performing a sequential search, which is infeasible for large volumes of data. For this reason, I have relaxed the intermodal connections in favor of a clear division of the visual and textual pipelines. Although effectiveness can be slightly compromised, in this way the online complexity to compute the final matching score used for ranking the images is collapsed into a simple dot product computation that is very computationally efficient in modern search engines. In this setup, we can extract visual and textual relational features from the endpoints marked with dark period dots. They can be pre-computed in an offline indexing phase and then compared at query time using a simple scoring function, in this case, the simple dot product, if the features are pre-normalized. In this regard, in a recent work, I introduced the TERN architecture, which stands for Transformer Encoder Reasoning Network. This is a detailed insight of the TERN architecture. TERN employs transformer encoder modules both for visual and textual processing pipelines. However, the visual and the textual pipelines do not communicate until the very end, where the features are projected to the same common space. This makes it possible to use this architecture to separately forward the visual or the textual pipelines for producing offline and online features needed for an efficient search. The feature similarity is computed through standard cosine similarity, or dot product of normalized vectors, and the model is optimized using the same previously introduced hinge-based triplet ranking loss function. The last transformer encoder layers share their weights, but this is used only during training phase for regularization purposes. The transformer encoders contextualize these descriptions and use the CLS tokens, ICLS and TCLS, for images and text respectively, to grow some global information intelligently constructed from the actual context through the same self-attention mechanism of the transformer encoders. The visual and textual CLS tokens are used as visual and textual output features. I used the NDCG metric with relevance computed on the sentence similarities using the SPICE and RUG-L metrics. Differently from RUG-L, SPICE relevance captures more semantic aspects, since it is a measure defined over the scene graph built over the sentence. I used the MS-COCO dataset that comes with 5 human written sentences for each image. I measure these results by performing sequential scan of the entire test set for each possible query and averaging the results. The TERN architecture reached best results using the SPICE relevance on 1K and 5K test set against the state-of-the-art architectures that employ separate visual textual pipelines. On the 1K test set, also the RUG-L relevance obtains the best results. These results demonstrate the power of self-attentive relational models, even in cases when the cross-modal links are lacking. These preliminary results on effective relational visual and textual features are targeted towards efficiency aspects to build scalable cross-modal retrieval systems. Now the challenge consists in finding effective ways to index these extracted representations. As far as textual or visual features with fixed dimensionality are addressed, standard visual features indexing approaches can be employed. Many works index these features using text-based retrieval systems using the power of inverted lists. In these scenarios, many works try to quantize and sparsify the visual features for use in textual systems with inverted indexes. Without going too much into details, methods like scalar quantization or deep permutation start from a dense float vector of a fixed dimensionality and obtain a sparsified integer vector usable in inverted lists. Each non-zero vector dimension is converted into appropriate term frequencies for that image, that in this case plays the role of a textual document. Given the flexibility of the Tern architecture, Tern can process and output features of contextualized regions and words, other than global fixed-sized relational-aware features. Given that, another possibility is to use a bag-of-concept model, a method similar to bag of words, in which words and regions are assigned to a set of predefined abstract concepts. Abstract concepts, as in the bag of visual words model, can be obtained by clustering. In this case, we cluster all the MS-COCO regions and words in output from the Tern architecture. Abstract concepts have an abstraction level where they have lost any modality information, so words and regions here are perfectly comparable. Every region or word is represented with respect to the predefined abstract concept, using either soft or hard assignment. In these experiments conducted on MS-COCO, I did not use an index. I studied the effects of the sparsity of the produced features, comparing them with cosine distance. Sparsity, in fact, is a key requirement in inverted lists. The results are reported for sentence-to-image retrieval, denoted as IR, and also for the image-to-sentence retrieval task, denoted as SR. In these graphs, we can see how the performance degrades when the sparsity of the vectors is increased. On the left, we can see that depermutation and scalar quantization approaches working on global fixed size relational features can maintain good results even until 75% of sparsity. On the other hand, on the right graph, we can see that the bag-of-concept model with soft assignment working on fine-grained region-word contextualized features achieves lower absolute values, and this seems overall more strained when increasing the sparsity. The problem with the bag-of-concepts model is that we are not able to deal with context shift, and we cannot natively deal with relational structured representations. In fact, the bag-of-concepts can deal with entities, but not with the relationships connecting them together. To conclude, in my PhD research work, I am trying to develop effective and efficient systems for relational cross-model retrieval. I started from visual relational retrieval using the novel RCBIR task as a benchmark, created using challenging synthetic images from the Clever dataset. Then I moved to cross-modal sentence-to-image retrieval on real-world images using state-of-the-art self-attentive models to produce contextualized and relational-aware multimodal features. I started experimenting with the efficiency aspects for the relational multimodal retrieval systems, using both fixed-sized relational features and variable-sized sets of contextualized features. In the future, I will continue with the efficiency aspects, moving towards query timing using bigger datasets. I am planning to develop custom indexing structures able to explicitly embed relational insights for the indexed elements. Also, I'm currently working on an extension to the Tern architecture able to perform weak supervised region-word alignment. This novel architecture is able to output interpretable region and word embeddings in the same common space, and it can be used as an effective feature extractor to test these novel indexing structures working with variable-sized set of contextualized features. It will be interesting to learn indexes directly from data, and finally, it is worth exploring full relational approaches without relaxations in the re-ranking phase. In fact, during the re-ranking phase, we deal with a much smaller subset of elements. Hence, a sequential scan can be executed with a relatively small impact on the overall query times, especially if inference is performed in batched mode on GPUs. This concludes my presentation. Thank you for your attention.